A very warm welcome to you all. Great to see some lovely new clients, lots of familiar faces, and also a special hello to my marketing colleagues from Australia, the States and Singapore. Thank you all for attending this morning. Our speaker this morning was born in New Zealand. By the age of 15, Michael Trousdell already knew he wanted to specialise in engineering. His interest had been sparked by a title in National Geographic, How Things Are Made, and this also coincided with him securing a job at an elderly person's home. As an orderly, working from the age of 15 to 18, Michael became interested in medicine and health. He subsequently attended Auckland University studying mechanical engineering and specialised in the design of medical products, initially working to design respiratory devices. After completing his degree, Michael travelled for a while, which influenced his passion in the environment, snowboarding in the snowy peaks of Wyoming, and then subsequently spending time in and around the islands of Thailand. Michael's appreciation of the beauty of the natural environment continued to grow. Arriving in London in 2001, Michael, not surprisingly, really did not enjoy the cold, grey, damp weather. So he jetted off to sunny Spain. After lying on a beach for a month, he soon realised that he was not really picking up the command of the Spanish language as he had anticipated, so he enrolled in some classes. After 3 months of Spanish classes and many failed attempts at interviewing in Spanish, he finally secured an interview at Gamesa, which is one of the world's largest wind farm manufacturing companies. He secured the job on the basis that he had learnt enough of the language in such a short period, and his new employers believed that he would learn more in the coming months. They duly set him off to a construction site where he would soon learn to speak proper Spanish, naturally. Being completely immersed in the construction site and the language, Michael subsequently managed the construction of wind farms from 2002 until 2007. He felt he needed a change after years in the wind farm industry, and whilst he could have stayed in Spain and progressed to head office, he was inspired by a talk by Chris Lubekin, one of our Arup fellows, then leading the Foresight and Innovation team, who spoke at an Architecture 2030 webinar in 2007. Duly inspired, he jumped onto the Arup website to learn all about our firm. He then proceeded to hound Arup HR, desperate to come and try and secure an interview with us here in London. After a few unsuccessful attempts, he finally arrived and was interviewed. He then secured a position. Since 2007, he's been involved in an array of projects, including BBVA Bank, designed with HDM in Madrid, Shantou Medical College, again designed with HDM, substation heat recovery with National Grid, Sky Central, Monument Building, and more recently Lord's Cricket Ground, notably the Warner stand, which just opened to the public. In the last 2 years, Michael has been central in expanding our smart buildings proposition and allied related research. So, without further ado, I really am very happy to pass you over to the very lovely and super talented Michael Trousdell. Thank you, everyone.
Thank you, Farah, and good morning, everyone, on this unfortunately not so sunny day. At least we've all got coffee and croissants to keep our personal energy levels up, even if we can't rely on the sun this morning. Now, when I set about researching for this talk, it really struck me how important the built environment is in the energy transition that's happening around us. And if there's one takeaway I'd like us all to leave with at the end of this talk, and that's to have a shared ambition to really be part of the change that's needed. Now, today I'm going to tackle three sort of main headlines. I'm going to give some context by talking about how we've used energy through history. And then I'm going to talk about where energy comes from, what the primary sources of energy are, and present some of the relative merits of the different types of energy that are available to us. I'll then conclude with my personal views on what us within the built environment need to do to respond to this challenge that's set by the energy transition. So what's the fuss about energy? Well, at a fundamental level, nothing of value happens actually without organised energy input and material use. So this means that the economy fundamentally relies on energy, and it's also actually inherent in anything of value that happens. Energy comes in many forms, but it can be converted between. The inherent structure or chemical structure of a piece of wood, solar radiation, or a weight at height all have energy inherent within them. But I think it's more useful to think about how we interact with energy in our daily lives. Living organisms on planet Earth interact in a few main ways with energy, and Homo sapiens are no different. First, we use energy for temperature control. In the first instance, with our bodies, but increasingly with a plethora of gadgets such as this Dyson fan on screen. We also use energy to produce light, like this deep sea fish does. And we use energy for movement, mainly with our limbs, but of course increasingly with a diverse spectrum of complicated machines, such as these car-building robots. We also use energy for data processing, and naturally that is constrained to what you can do with your brain and your nervous system, but us Homo sapiens have increasingly used a plethora of computer technologies to process and store and communicate. So now a quick pause to mention a couple of definitions. While we often use power and energy interchangeably in conversation, they're actually quite different concepts. Power is the rate at which something uses energy. And in the book Sustainable Energy Without the Hot Air, Professor David Mackay did a great job of humanising these two units. So first, energy. We're all familiar with a kilowatt hour. That's a unit of energy that appears on our electricity bills, and we pay sort of 10 to 15p for a kilowatt hour of energy at the moment. It's also a human scale unit. Now, in a day, a human can deliver about 1 kilowatt hour worth of work. So it's important to keep in mind, though, that to deliver 1 kilowatt hour worth of work that's useful, you need to consume about 2.5 kilowatt hours of food. And that's this principle of the difference between energy use and primary energy, where the energy is sourced from. As I proceed, when I mention energy, what I'm referring to is this primary energy, or the sort of fundamental energy that is needed. Now, relating power to energy, you can do that quite simply with the light bulb. If you leave a 100-watt light bulb on for a 24-hour period, it will use 2.4 kilowatt hours. That's about a person day worth of energy. So our sort of power rate on average is similar to a 100-watt light bulb. But of course, our rate of power output can change. When we're sleeping, it's about half a light bulb, and Usain Bolt, when he's sprinting, has an astounding power output of about 2,600 watts, or 26 light bulbs. And clearly for us mere mortals would not get anywhere near that. We'd be more constrained to around 10 light bulbs worth, just for short periods of time. We're all familiar with horsepower. That's about 15 person power. So now, equipped with those units of power and energy, just run through very quickly a short history of the way Homo sapiens have used energy in the past. So before 100,000 years ago, we just relied on food and the energy that we could process through our bodies. But at that point, we sort of adopted widely the use of fire, and that increased our sort of energy allowance available, but just for temperature control. So researching this talk, I had the assumption in my mind that the advent of agriculture would have changed our sources of energy. But it didn't actually change the sources. All it did was increase the reliability of supply through improved storage mechanisms, including actually using ice from mountains some 10,000 years ago. And this idea of energy security being important remains a fundamental sort of consideration in energy policy today. This simple reliance on combustion and moved ice for temperature control remained the status quo all the way through to the turn of the 20th century. It wasn't until 1910 that refrigeration systems overtook from imported ice from Canada as the main source of cooling in New York. Now, today we have a huge amount of power available for temperature control. To give context, One Canada Square in Canary Wharf has a cooling system with a power rating of 21 megawatts, and it can use, therefore, 100 megawatt hours worth of energy in a typical day. To put that in context, that's the equivalent of 100,000 person days worth of energy, and that's obviously just one building here in London. Now, light we've also been controlling since we got control of fire. Even 75,000 years ago, humans had figured out how to put a little bit of animal fat and grass into a shell, sort of carry it around. But clearly that was very expensive. You were diverting food to combustion, so you'd only do it if you really had to. And not much changed, really, through history. Obviously, candles made it a little bit more convenient some 5,000 years ago, but it remained a very expensive resource that was used in a limited way. With the advent of electricity, that all changed. And the important factor really was cost. A Yale professor, Bill Nordhaus, estimates that the difference in price between Edison's sort of light bulb and a candle for the same light output is a factor of 20. And when you look at lighting today, the cost has gone down again by another factor of 20. And lighting does really pervade the 21st century living, from illuminating our city skylines to being used for diverse things like eye surgery or many manufacturing processes and navigation. The category of movement just relied on our limbs and our bodies all the way through to about 5,000 years ago. For the first half of the sort of the advent of agriculture, it was all just person power. And this domestication of animals obviously increased significantly the amount of energy available to us. We could, by having 2 oxen, as shown on screen here, you effectively get about 10 person power worth of energy available to that one person, with a lot less effort obviously involved. Just thinking about the great expanse of the Roman civilization with all those cities and roads and complex big armies, all of that was built with obviously a lot of human ingenuity, but these very constrained sources of energy from wood, person power, and a little bit of animal power. Now, the big change that came about 250 years ago was the invention of the engine. And what that did was convert heat, and we had loads of it obviously available, into movement. And it was that fundamental change, that idea, that really sparked the whole industrial revolution. And putting an engine on wheels, actually creating the car, meant that we had cars competing with horses, and even this 1908 Model T had 20 horsepower or 300 person power, and the fuel tank had 400 person days worth of energy in it and could obviously be very quickly refilled. And today we have an enormous amount of energy or power available for movement, with the most extreme being, of course, rockets used for space exploration and warfare. And this rocket on screen, the F9, consumes fuel for just a short 5 minutes, but at a rate of 25 gigawatts. And to put scale on that, that's half the capacity of the peak electricity grid for the whole of the UK, or 25 huge power stations all running together. Putting that into the human scale, it would be sort of 10 million Usain Bolt sprints worth of power. So clearly a lot. Now, to data processing, that was very constrained from an energy perspective, just in our brains and nervous system, until some 5,000 years ago, where we started writing. And that obviously created recording of data, external way, but for a very small elite of society. The printing press really just changed things by expanding availability to a much broader spectrum of the population. But the energy involved with sending messages around was actually very significant. Through history, it involved a lot of horses and men riding around, and obviously a few carefully trained pigeons. But all of that changed with the advent of the telegraph, where we could run communication lines of a great distance and therefore significantly increase communication, but importantly, even more significantly reduce the energy cost needed to get a message from one place to another. And since the 1940s, we've had a hugely expanding availability of energy for processing data, storing, communicating, with computing now central to our lives. So now, having concluded the use of energy, where did the energy come from through history? So 100,000 years ago, we just had 1 million people on the planet, and we used food as our primary source. About 2,500 tonnes of food was consumed per year by that little population. But notably, probably twice as much wood and weight would have been burnt, meaning that we actually used more energy in wood than we did from food. 10,000 years ago, population had grown, but the energy sources hadn't changed. 5,000 years ago, we had that addition of animal power in the movement category, but it remained a small fraction of our sort of energy that we'd co-opted for our daily lives. 1,000 years ago, now with 400 million, the big expansion around the Roman Empire of population, still a very similar energy mix, but with obviously a much larger animal power component and a little bit of water and wind power available to the elite. Now to 100 years ago, our energy use was expanding very quickly, with coal overtaking wood as the main source of heat, but notably oil at a point of almost overtaking from animal power as the main source of energy for movement. Now to today, and our energy system is dominated by fossil fuels. 80% of our energy comes from coal, oil and gas, pretty evenly split between those three. And we have two new sources of energy in the mix, nuclear and solar, which were sort of invented in the 50s and expanded. Solar was used in satellites in the 60s and 70s, and nuclear was expanded in a similar sort of time frame. But they remain relatively small portions of our energy mix, solar especially, the little dot up on the top there. It's important to note, though, that this sort of great expansion in energy use is quite unevenly distributed around the planet. An average American uses 200 kilowatt hours per day. And for instance, an average Turk uses about 45 kilowatt hours per day. But to put that in the context of the history of energy use, 200 kilowatt hours, that's the equivalent of 200 sort of energy servants working to improve an average American's day. So a significant amount of energy that's available. Assessing the relative merits of the different sources of energy used today is very complex, and the cost of energy and the security of supply have been key drivers in our choices for energy for thousands of years. But more recently, environmental concern has come to the fore. A key environmental concern that we have in front of us is obviously climate change. The Intergovernmental Panel for Climate Change has documented the life cycle carbon emissions for generating energy from all the major types. Now, when you plot our sort of common types of energy against the data from IPCC, you have a sort of broad spread coal, the most significant impact on the right, but the low carbon options all actually huddled very closely together there, very near zero climate change impact. And that doesn't really give a full picture of the wider environmental impacts that these energy systems impose on the planet. So the chart here on the screen summarises sort of other environmental impacts that energy systems impose. And this is an extract from an internal research project that we've been developing, looking at 35 main types of energy and what their sort of wider environmental impacts are, so that can be sort of understood and provide further context to the climate change impacts. So when you plot climate change impacts on the x-axis, and then these other impacts up on the y-axis, you get a much more nuanced view of the sort of relative merits of these types of energy. So looking at the low carbon options, large hydro actually has a little bit more climate change impact than small hydro, and quite significant wider environmental impacts to consider. You can see solar and wind top there right down in the good corner with very low impact across the board. Now, there are many types of fossil fuels, and they're clearly not all equal, both in their climate change impact but in these other impacts. And it's clear looking at the chart here on the screen that we want to have less coal, less tar sands, less peat. It's interesting to note that this assessment sort of showed that shale gas is actually quite similar to onshore gas, putting those two categories as the sort of least bad fossil fuels available to us. Now, the coal industry has been promoting carbon capture and storage as a technology to keep coal in the game. And this technology effectively uses some of the energy from the power station to push the emissions from the power station down into the ground and store them. And this still remains to be proven sort of economically, but there's also a key sort of environmental consideration to keep in mind. And that's that when you apply carbon capture and storage, yes, you save carbon emissions, but you need to use about 20% more coal to get the same energy output, and so therefore you get about 20% more wider environmental impacts. So that puts coal with carbon capture and storage still at a very negative place in this chart with significant wider environmental impacts to consider. Now, applying carbon capture and storage to gas is a much more interesting proposition from an environmental perspective, putting gas in a similar, if not better, position to biomass. And then applying it to biomass actually shows an even more interesting story where there's potential to actually have negative climate impact. Before we get too excited about the idea of biomass and carbon capture and storage, there's a point of scalability to consider. And a lot of the energy types out there, hydro, tidal, geothermal, and importantly biomass, are all limited resources, and collectively actually they only add up to about 15% of our current primary energy use, and we can't expect that to expand very much without very significant environmental sort of impacts. So that leaves solar, wind, nuclear, and of course our existing use as fossil fuels as the energy sources that can scale to our needs. So going back to the types of energy we use, that means there are a few that we can't really expect to change too much. We don't want to go back to being animal power led or relying on food, and biomass and sort of hydro systems we can't expect to expand much. Clearly we want less coal and less oil, but I think it's right to say that we want more wind, more nuclear, more solar, and actually more gas, but with this carbon and capture and storage. Now, there's a lot of sort of excitement about the energy transition that's happening, and this is a news sort of blast that went out in May last year. Germany, 100% renewable power. And it's important to keep in mind actually this happened on a Sunday afternoon, very low power demand, on one of the windiest, sunniest days of the summer last year. So it was effectively a Usain Bolt sort of sprint moment for the German electricity grid. Now, the much harder peak to deal with is actually the winter heating peak. And the excitement about that 100% renewables was just about electricity and at a low demand. So that is the sort of scale that we're looking at when they're saying 100% renewable power was achieved. Winter peak is about 6 times what you have for the electricity grid at the moment. And to give a sort of scale of how much bigger that is, there's been in the news recently the largest battery installation is going in Adelaide in Australia, and it's got a capacity of 100 megawatts, 129 megawatt hours worth of energy. And to meet just 1 hour of the winter peak heating with battery installations of that type, you would need 3,000 of those installations. To meet a day's worth of energy, you would need, therefore, about 70,000 of those installations. And the cost involved with that is just enormous. It would cost about 2 trillion euros to build that many batteries, and that's about half of the GDP of Germany's economy. So clearly not something that we can expect the energy system to pay for. It's also worth mentioning that it would be 100 years worth of factory output of batteries at the rate that we produce batteries at the moment, just to meet the peak in Germany alone. And so again, the scale of the challenge is very clearly defined by that. It's also important to keep in mind it's not just peak power that we're trying to deal with. We want to have low carbon emissions for the energy on average over the year. And the German energy system is still dominated by coal and oil. About half of their energy comes from those two sources. And the renewables that everyone's very excited about, solar, wind and hydro, just make up 4% altogether after decades of investment and expansion. So now to the present and the transition happening around us. Within the complexity of the current situation, there are two key changes that I think will have a big impact on our energy system. The first one relates to the cost of energy, and the book Burnout by Dieter Helm presents really interesting analysis on the geopolitics and sort of macroeconomics of the energy system. But a key conclusion that he reaches is that energy costs are going to go down. And the reason why he says that is, first, there will be an oversupply of increasingly unwanted fossil fuels, making fossil fuels cheaper and cheaper. And then second, the capital cost for renewables and batteries is going down, and renewables have almost zero marginal or operating costs, because obviously you don't have to pay for the wind or the sun. So what that means is that we can expect our sort of energy system to move from a cost model that's dominated by cost for energy to a model that's dominated by paying for capacity. So we're already familiar with the sort of standing charge that you pay. It might be about 10% of your sort of energy bill. But Dieter Helm's analysis suggests that in the future, the standing charge will go up and the energy cost will come down, but overall the balance of what we pay is likely to actually be lower. The second big change relates to automation. And we're automating more systems for two main reasons. The first one being the cost of the hardware involved with automating. It's now very cheap to have sensors or actuators directly connected to the cloud, exposing them to increasingly advanced software that is also getting cheaper and cheaper. So this means that we can set our energy system up to be controlled by machines and give those machines increasingly sort of complex sort of tasks, so saving energy while meeting our diverse business and personal requirements. So to the four uses of energy and what this will mean. It is realistic to expect that solar, wind and batteries could supply our energy needs for data processing. And that's because the energy we use for data processing is relatively small as a fraction of our own overall energy use, and it also follows a relatively predictable daily cycle, which works well for renewables and batteries. Our lighting requirements also follow quite a predictable daily cycle, and therefore it follows that batteries and renewables could provide our lighting needs most places around the planet. Movement's more complex, and it's clear that some modes, such as aviation or large shipping, will remain fossil fuel driven for some time. But for machines and factories, many are already electric, and there is a trend to automate and electrify. Now with road transport, I think the Elon Musk camp that are backing batteries will win out. And in the first instance, because electric cars simply perform better, they are much safer, and they're also cheaper to operate. But there is an energy system reason to expect batteries to win out over hydrogen. Now this is because the life cycle efficiency of a hydrogen storage system relative to the life cycle efficiency of a battery storage system is very different. you need to use about 3 times as much energy to fill a hydrogen tank compared to filling a battery. So therefore it follows that you would need 3 times as many wind turbines if you were to use renewable power to fill hydrogen, with the obvious increase in cost. And it's this likely higher cost and effectively a cost penalty that's likely to keep hydrogen vehicles in the experimental category for the foreseeable future. Now, with temperature control, we are seeing a trend towards electrification of heat, and we already use electricity for cooling. And for mild climates, such as, say, the Canary Islands or South Australia, where this new battery system is being installed, we could expect in the coming decades for the energy system to move towards being renewable and battery powered to deliver our temperature control requirements in those mild climates. But for anywhere with a more extreme climate, be it either really hot or cold, we can't expect this peak power requirement for heating to be met by pure renewables because of the huge investment in batteries and in renewables that would be required to meet this peak. And this is effectively exacerbated because you can get periods of a week of low wind, and the solar availability in the UK or Germany in winter is actually about 10% of the solar energy that's available in summer. So you have effectively much more energy use and much less renewable energy available. So the fundamental challenge the industry faces is meeting this peak demand and doing it without the environmental impact. And what we need to do to achieve this is to rethink how we design, construct and operate our buildings, and importantly our infrastructure. And there's no simple answer to this challenge. The solutions have to be right for all building types, existing and new. But we don't have to wait for consensus on this. We can start now on the projects we have in front of us, one building at a time. And I'll leave you with a quote from Margaret Mead, the American cultural anthropologist. "Never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it's the only thing that ever has." Thank you. So, questions, anyone?
My name is Chris Couture. I work for the Nichols Group. I was very interested in your presentation today, particularly the graph that showed where you thought the world was going in terms of renewable energies. And I noticed that you had water and it didn't move up.
Yes.
So could you explain a little bit about why you thought that water wouldn't be a primary energy source in the future?
So hydro dams at the moment produce a small fraction of energy, around 3%, and there are plans to expand hydro in Asia and Africa, especially in Africa actually. There's quite a lot of potential. But even if you did dam all of those rivers, you might possibly double the capacity globally, so you'd take it from 3 to 6%. So we can't expect hydro to make a big impact. And we also need to keep in mind, if we did double the hydro capacity on the planet, there would be huge adverse social and environmental impacts to consider.
Tidal? Is that in the same bracket?
Yes, even smaller actually. And David Mackay's book, Sustainable Energy Without the Hot Air, did a great job of sort of setting them all out in the context of the UK. And you see, for the UK and then also scaled to the planet, that all of these energy sources are small, sort of sitting as single-digit percentages.
Thank you.
Hello.
You focus mostly on meeting demand rather than reducing demand. Can you comment a bit more on the role for energy efficiency?
That's a very important factor, and obviously most significant and most useful in improving against this peak winter demand. And personally, I am quite hopeful about the future of efficiency, not so much through behavioural change of people, but more because of the opportunity that automation brings. I think we will be able to put little monitoring and control devices on a very low cost to drive efficiency. Now, there's also clearly a challenge for the built environment, the fundamental sort of design of buildings. The facade performance has a big impact on improving efficiency and improving the sort of peak use of energy in winter. Hello.
You showed us the graph where you had sort of, we need more of this and less of that. And
Yes.
in the more category, you had nuclear power.
Yes.
Could you just describe the research that's been undergoing here at Arup in terms of understanding that?
Right. So Arup does have some involvement with the nuclear industry. We work on some modern power stations, and increasingly the industry is heading towards small modular reactors. I think there's approximately 80 designs being put forward from around 40 countries, and there is a sort of an ambition within the industry to offer much safer, much cheaper nuclear power at the small scale. Whether that is proven, whether that actually eventuates, remains to be seen. But noting that we really can't rely on renewables in cold climates, we're left with carbon capture and storage, gas, or nuclear as the scalable options. And so I think we can't afford to discount either of them really, noting that they both have significant challenges.
When you talk about nuclear, you're talking about fission reactors, but how does your calculus change if we get some fusion ones soon enough?
That would be fantastic, wouldn't it? Yeah, if we got nuclear fusion reactors, our power and sort of availability of energy at very low environmental impact would expand greatly. But again, it's very hard to predict when or if that will happen. So
So there's no magic bullet. You've got a magic bullet right there. That's your answer.
Well, sure. I don't have it, but the scientists, of course, there are obviously a big group of very talented people trying, and good luck. I really hope they do get there, but we can't rely on it, I don't think.
You talked about very large grid-scale batteries. How about building-level batteries, either in residential homes or large office blocks, and also electric vehicles? What do you think of that as part of the solution?
So building-level batteries are great, and I can see them playing a part in the sort of energy market, which could be driven, as Dieter Helm sort of predicting, more by capacity as opposed to kilowatt hours of energy. And so putting batteries in is a good thing to do for an economic and a sustainability point of view, but it's going to help us with the daily cycles for running our computers and our lights, not for meeting our peak winter or our peak summer cooling or heating loads. Car batteries, great again, it's a small fraction of our energy system, but what's really great about car batteries, the primary energy used in the transport sector could halve if we moved from oil to batteries, because the system efficiency through is better. If we move to hydrogen, it would go from its current primary energy use to an increase to 1.5 times. Clearly, obviously, lower carbon options, but the amount of energy used would go up if we went from petrol to hydrogen. Okay.
One important factor on your graphic was population. We
Yes.
went for 1.8 million, I believe, 150 years ago, and we're like 8 billion now. So demand will increase potentially. So how can we factor this?
Yeah, population is the big multiplier for our energy use, and it was so start looking at the data from 100,000 years ago to 10,000 years ago, it just expands just due to population. And while efficiency, mentioned earlier, does improve things and we get more done for the same amount of energy, we can expect energy use to go up if population increases, as it's expected to do. So it makes it even more urgent and more important to deal with it.
Firstly, thank you very much for your very succinct and clear presentation. Having worked with David McKay shortly before his passing, I know he'd be very encouraged by your graphic presentation. But my question to you is in two parts. The first question is in terms of the development of carbon capture. It's something that seems to have fallen by the wayside of recent. I was wondering if you had any thoughts on how quickly that technology would need to come through in order to facilitate the increased use of gas.
So my personal view is there's been much too much focus on carbon capture and storage with coal, and we've really got to put that to one side. There's very little discussion even about using carbon capture and storage with natural gas, despite the fact that it's just as simple or complex to install as it would be with coal. Now, a new idea that has only really sort of entered my mind in reading this book that Dieter Helm published earlier this year. The big difficulty with carbon capture and storage is the cost. But if natural gas gets cheaper and cheaper because there's oversupply, that marginal extra cost to do gas with carbon capture and storage could come down. So that would be a sort of market driver. I also obviously hope that there's a carbon tax agreed, but I'm less optimistic about the political agreement needed for that than I am for Dieter Helm's prediction of the cost actually driving carbon capture and storage onto the market.
Well, first of all, I thought it was a really interesting talk that Michael gave, and I really liked the fact that he set out very clearly what the issues are with all forms of energy sources going forward, and where he thought the advances will be and where we should be putting most of our effort. And I particularly enjoyed the fact that he broke a lot of myths about fossil fuels, so a lot of food for thought. What I would like to see is energy sources that do have a low carbon footprint, and somehow, such as nuclear, we can reduce the actual environmental impact that it provides at the end of its life. So if we can do something about that and bring that down, then I'm hoping that all forms of renewable energy, including nuclear, will have a part to play in the future.
I thought what Michael did was an amazing job distilling the complexity of different methods that we might be generating energy and power in future. There are so many alternatives, all of which have got pros and cons, and trying to work out which are best from that and which are going to best suit needs, I thought was really, really clearly expressed. I think there are other issues around this, around some of the politics and the acceptability and perception around it as well, and around how we start to change patterns of demand into it, but a really interesting and thoughtful presentation.
Obviously I've known Mike for a long time, and I've spent quite a lot of time discussing these issues with him. I suppose what kind of fascinates me is that it's not straightforward, and Mike is sort of over the years has kind of, he's changed his position slightly on certain things, but as he's become more knowledgeable about stuff, and he's continually sort of probing and trying to understand the issues in a sort of deeper way, and he has it's very thoughtful, and it's a very cohesive story, I think.